Okay, guys, let me share the PowerPoints again. The concept of the concept of acid and bases. So we went through three concepts. The first one was Arrhenius, and it failed, and it's really deleted. Arrhenius came to the conclusion that any chemicals that had protons in aqueous solution, it's an acid. Any compound that has hydroxide OH, that's a base, and I told you that's not always true. Not every chemical has OH. Not every chemical that's OH is a base. We have phenol, benzyl ring connected to the OH, the hydroxide. This is a phenol or hydroxybenzene. This hydroxybenzene or phenol is an acid. So weak acid is an acid. So not every compound that have OH has to be base. So therefore the concept from Arrhenius is deleted. The second, which is still alive and used heavily, concept of Bronsted and Lowry, the concept of donor and acceptor. It's based on that the acids are protons donors when they dissociate inside the aqueous solution, inside the H2O as a solvent. They dissociate and they can donate their protons. The bases, on the other hand, they are acceptors for those protons from the acids. So the concept donor acceptor is really valid and make a lot of sense. It does not matter. It doesn't matter that a base has an H like ammonia. Ammonia is a base, but it has a hydrogen. So you cannot tell ammonia has a hydrogen is a base according to Arrhenius. That's nonsense. And you cannot tell phenol has a hydroxide. That's a base. That's not true. Phenol has hydroxide, but it's an acid, not a base. You see what I mean? So that's this concept for Arrhenius deleted because of the fact did not really take the concept of what is the function of acid, what's the function of the base. Acid always donating its protons and the base always accepting those protons. Now, the idea is acceptor donor, then we have to look at the what happened after this donation and acceptance of those protons. This is an acid here. If you look, let me maybe make it thicker here. I want to make it thicker seconds. Can you see my the pen there? I think you can see it. Okay. So that's an acid here, and this is a base. Okay. So the acid with its proton here, the proton will be given to this base. So then the acid at last, here it is left over of the acid. And this is after donation of the protons, the base become pH because it's accepting this proton. Now an acid that had lost its protons, correct? That's called conjugated base. This is called conjugated base. So what is conjugated base? Conjugated base actually is an acid. It was an acid. Actually, it's an acid that had lost its protons. So instead of HA, now it's A. So the H is taken by the base. And the base, the conjugated acid, is actually was a base that's accepted what? This proton. So let's do it this way here. H HA is always in conjunction with A minus. And B, correct, is in conjunction with pH positive. So you can see that. So this is negative. So the conjugation between acid and its, this is acid A, and this is, if you have an acid here, you'll have a conjugated base. Conjugated base. It was an acid that had lost conjugated base. Conjugated base that,
Dr. Tia,
yeah.
I don't see any of that stuff you're writing. It just has the PowerPoint screen up.
You don't see it? Why is that?
It just says acids and base characteristics. I don't see anything that you're writing.
Oh, really? Let me see what's happened. Let me stop sharing.
Unless I'm not inside the meeting.
No, you aren't. Yeah, you are correct. You are in the meeting. So hold on. Share.
Okay.
Let me repeat this, whatever I said. PowerPoint. Share. Can you see any writing now?
Yeah, I can see what you're writing now, but anything that you wrote before, it wasn't showing up at all. I can
Oh,
see
really?
that you circled the HA on
Okay,
the
that's
acid.
good. That's good. So I'll just
Okay.
circle those again and then change the color of circles here. So those here, this is an acid with its conjugated base. So the Bronsted-Lowry concept of acid base, being acids are donors of the protons and the bases are acceptors of those protons. That's the concept of Bronsted and Lowry extended to the other concept that's when the acid donates its protons, something will be left out of it. There's something is out of it called conjugated base. So if you have an acid, if you have this an acid here, you should have a conjugated base. A conjugated base, nothing else than just an acid that lost its protons, or that really not lost, but that donated or has donated its protons. So now the base here is acceptor of this proton, this base here. Yeah, those. So the pH is you have a base. When the base is accepting these protons, it's become positive. So this has a positive sign, and this one has negative sign. So the pH, the base that accepts the protons, called what? Called conjugated acid. Conjugated acid. So we have acid, okay, with its conjugated CON. Just I'm not writing the whole thing. I'm just conjugated base plus base plus and this in conjunction with conjugated acid. So here it is. So the base, when it's accepting this proton, becomes, with this new proton attached to it, it becomes a conjugated acid. And the acid, when it donates its proton, it becomes conjugated base. So that's what those two together. And I want just to go and take this one out, or this out here. Let's see if we can clear all. And I'm gonna share something else. I want just to let you know, this is now late for the semester, but uh, we will have Zoom. Today we get an email from administration. We're not, we will have the opportunity to use both, but I like Zoom than WebEx. You see, WebEx, it's very cumbersome to deal with a lot of, it goes a lot of steps. So I'm gonna share something else. I have to get out of sharing and then come back again, and it's very cumbersome. So I want to share some of the worksheets. Let's see. Let's share this one here. Okay, so let's take a couple of those and tell me which one is an acid, which one is a base, and which one conjugated acid. So I'll put this one here as a key. So acid, okay, and then conjugated base, and then base, conjugated acid. So let's try maybe two of those or three from A to H. From A to H, tell me which you like. We'll take three and then let's decide which one you like, guys. I'm not picking anything.
Letter E.
Letter E. Okay,
Yeah.
here it is. So letter E, you just tell me which is an acid. We'll put different color now. I think we need another color. So blue, maybe. So which is an acid, which is a base, which is a conjugated base, and with its conjugated acid. So let's start. The first one is, this one is what?
Would that be an acid?
That's the acid. Why? Because it donates, the protons is gone out of it, correct? And that's left
Because it
over
has.
out of, that's what left out of this acid, correct? So this one has to be an acid because it's a donor. So this is A. That's correct. Now, if I have an acid, the anything will come out of this acid is had lost, had lost its what they call it, its proton. That's the acid donates, and after donation you get this compound here. What is this? Will be what? A conjugated what? Conjugate what? Conjugate base. Conjugate base. Yeah. If that's an acid, this one will be what? This one will be base, correct? Acid always react with the base, not with conjugated acid or bases. So just direct with the base. So then what will be this one here?
Conjugate acid?
Conjugated acid, so Ca. So now we have a conjugate acid base, and then whenever this base is getting these protons, accepting those protons become positive, and it will be conjugated acid. Okay, and the acid, once losing its protons, or this chemical compound becoming without the proton, it will be conjugated base. Okay, guys, this is number three, number E, correct, E? So let's take another one. Okay, guys, any question about this? Any question about this? Any question? Any question? So let's take this one out. And just okay, so what's next? Which one? Hello, which one? We, two. We don't have to. We have B. You mean B?
Yeah.
Okay. Tell me where's the acid? Where is the base? Oh, sorry. So which is the acid, which is the base? In B. Look at which one has donated its protons, even it's just one proton. Which one's accepting this proton? So come on, guys.
I got a question for you. Would it be the one that
Yes.
has the negative that's accepting the proton?
No, a proton, an acid
The
can
one
be
that, like,
an acid can be negative or positive. The charge does not really saying anything, but losing the protons will make the acid vulnerable. It's just exposed, so it's losing one of its protons. Then it's what will be having if you lose, if this acid loses the protons, it become negative. It should be. We have seen in the previous example, correct? We have seen it in the previous example. That's in E. You see, have you seen E? The HSO3, but it is what HSO3 came out with the sign, correct? So HSO3 is an acid because it donates its proton to H2O. H2O is a base because accepting this one here. By doing this, the HSO3, correct? That's hydrogen. It's not sulfuric acid. It's not sulfurous acid, but this is monosulfurous acid. So this acid will lose its one single proton does it have, and it will become what? It will become negative. So you see all the time, it does not matter, is see here E. So always when you lose the protons, the outcome of this loss will be negative. So here it is B, you have this one here, has two protons, it lasts one. So this one here, it lasts one means you have one positive charge is down, so therefore it will a whole molecule will appear negative because it lost one of its protons. So this is an acid A. This one will be acid cannot have the same acid conjugated acid. No, if it's an acid, it will be conjugated base. Okay, then let's move to another color. And this one will be a base. Okay, and then this one here will be conjugated acid. A conjugated acid, remember, don't worry about the charges, but worry about the definition. what is a conjugated base? Well, conjugated base, actually, it was an acid that lost one of its protons, correct? That's very important. What is conjugated base? It was actually the opposite. It was not a base, it was an acid. When it lost one of its protons, then its acidity characters is damaged. So, correct? So it will have a negative charge because one of the positive protons are gone. So now, on the other hand, what is a conjugated acid? It's not an acid actually. It was a base that had gained this proton from the acid. Correct. So this one will be a base, and this one will be conjugated acid. So now, if you wish, so this one here, an acid, correct? It does not go the conjugated acid. An acid goes all the ways with a conjugated base. And the base here goes conjugated acid. Okay, guys, one more, and then we'll go for the next topic. Okay, what the third one? Which one you like? Which one?
Yeah, do the third one, C.
Okay, so C2, this is acetic acid or ethanoic acid, but in the way written is in a molecular formula, not the structural formula, but structural formula will be looking CH3, CO, OH. That's the vinegar we titrated in the lab. If you recall the lab, we titrated the lab. So this is all two oxygens here. So this is acetic acid. Acetic acid will react with the base. Now this is acid, correct? And this is what? This has to be a base. Now, what's about this and what about the other one? It turns out the acid is donating this H. See? What's remaining here is from this part here. Oh, sorry. This part is remaining after donation of this out. It's being donated. So this one will be what? A conjugated acid or conjugated base? Is this a conjugated acid or conjugated base? What you can, A or B?
Would it be a base?
A conjugated base, correct. Is not a conjugated base, remember, is not per se is a base. It was an acid, acetic acid, that had lost its protons. So this one had lost its protons. They'll appear so negative because it lost one of the protons. This acetate anion, correct? That's acetate anion will be conjugated base. This is very difficult concept for many students, even at the graduate level. So since some even people are taking master degree, I was helping them inside their thesis. So it is a very difficult concept, but you can always understand it in the way an acid that donates according to Bronsted its protons. The base is donor accepting these protons. However, when the processes between donation and acceptance, those protons, the one is accepting now become what is it was an acid that lost. No, the one is accepting it was a base that accept what these protons. So that will be conjugated acid. Becomes acid because it has accepted this proton. The acid that lost these protons is no longer acidic because it lost the protons, so it will be a conjugate base. It will be conjugate base, but actually it's not a base. It was an acid, but during the process of the reaction, it lost its proton. So this is Sb, correct? This is A, this is B, and remember B is H2O. It's accepting the proton here of the acetic acid, it's accepting this one here. So it will become H3O plus. That's a conjugated acid. So always acid will be accompanied with, so conjugate means accompanied with. So acids accompanied with conjugated base. And the base is accompanied with or grouped with conjugated acid. Base grouped with conjugated acid, which is accepting these protons, become acidic in character. And the acid, when it loses its protons, become less acidic in character, and it will be conjugated base or conjugate base. So I think that's enough for this. Let's share something else. Let's share the PowerPoint. I have to stop this and start sharing. As I said, it's a little bit cumbersome here with sharing here. So now we have this. We can go further and look at the acid-base character and concept. The third concept of this is called, we did Bronson and Lowry. The third concept is Lewis. So Lewis concept is based on the acceptor and donors, not the from protons, accepting and donating valence electrons. There are some compounds that have extra valence electrons. Okay, they have extra. They can donate. Those are called bases. Some acids, they have deficient valence electrons, not that many, so they can accept those valence electrons, and those will be called so-called acids. So acids are valence electron deficient. Bases are valence electron what they call abundant, or valence electron not deficient, but yeah, they have extra valence electrons. So that's according to Lewis. And one of the example here you can see, we can, I can give you one example here. Let me see what they have here. First, naming acid and base, we name those. But let's go and look at the example. I have to stop sharing and then go back and look, share what I'm sharing. I'm sharing my whiteboard here. Oh, sorry. That's an extra credit coming to you. So there will be another blood. Can you see that, guys? Can you see it? I'll announce it tonight. I got it from my friend here, Professor Mark Graves. So anyway, so there will be another blood drive coming. So the students, I'm asking me about this today in the lab, but there will be another one coming. So, but anyway, everybody is hearing about this blood drive? Everybody is hearing me? Yes,
Yes.
no? Yeah, so
Yes.
there is another one. The blood drive people, I mean, the Red Cross is really appreciating our donation. So, and we encourage our students by giving extra credit and good points So that will be good for everyone. It's a win-win situation. If I have time, no lecture, so I go myself too. I did donate it through the whole years, even when I was in the graduate school. You feel very happy we have, donated, participated, supported other people, the needy people. So anyway, so now let's look at this. Let's look at this and then we'll see. So we talked about this uh, acid base. We talked about the Arrhenius being the worst concept ever. And then we talked about Bronsted Lowry with the donor and acceptor of the protons. Definition of acid base based on the protons donation or acceptance. Then the third one is Lewis. Lewis with his group. Lewis had worked with a lot. Most of his time is with that structure, the structure of a chemical compound, covalent or whatever. Yes.
Are you writing anything? Because I can't see it.
No, I'm not writing anything yet.
Oh,
I'm just putting the whole thing together. Lewis came and put this valence electron stuff, donation and acceptance of valence electrons. Lowry and Bronsted, donation and acceptance of protons in aqueous solution. Lewis is donation and acceptance of valence electron in aqueous solution. So forget about Arrhenius. Arrhenius is obsolete and the whole concept is deleted anyway. So now, if I have, now I start writing here. Everybody can see? Everybody can see me? Yes,
yes,
no? So
yes.
now let me, okay, good, thank you. So let me get to this one here. I will draw loose that structure of ammonia, okay? Ammonia, so this is ammonia. This is ammonia here, NH3, and it has two unpaired or two non-bonding or two lone pair. So lone pair, non-bonding, anti-bonding, okay, all meaning the same thing. So this is the structure of ammonia. So ammonia, according to Lewis, that structure is a base. Why is the base? Because it has extra or excess of valence electrons can be used for any type of chemical reaction. So if I take color here, I'm circling now those two here. Those, although they have three single bonds, we have excess of VEs here can be used for bonding. So this is according to Lewis, this is a base. According to whom? To Lewis. So because it has excess valence electrons, it can react with um, some some compound that has least amount of what of valence electrons. So let's look, for example, the very obvious is here boron, B, H, BH3 boron. It's boron trihydride, boron trihydride. So boron trihydride, and this is ammonia. What's the chemical name of ammonia, please? Somebody will help me with this. What's the real name? Not the commercial name, ammonia, whatever. But this one, what's the name of NH3? This is boron trihydride. One is here. And ammonia is what? Nitrogen trihydride. Come on, guys, don't let me down now. Final exam are coming. Final exam is coming. In the lecture in the lab, final exam, I'll say. So nitrogen trihydride and boron trihydride. The nitrogen trihydride has a commercial name, correct? What's the commercial name, business name? What's the commercial name of it? Somebody will tell me. What's the commercial name of ammonia? Windex. Somebody has seen Windex? Somebody have used Windex? If you open the bottle from this carefully and waft the whole smell towards your nose, don't sniff too much of it. You'll bust, will bust out. It's a very nasty smell. But anyway, that ammonia or nitrogen trihydride, it has excess of valence electrons, correct? This one has deficiencies in the what? In the valence electron, does not have extra. So now this one here will donate. Let me just change the color. Maybe that should attract your attention here. This can be donated to the boron, correct? This will, because that's now the opposite of the Bronsted-Lowry. That's the acid always donating, and the base is always accepting. Here, the base is donating, and the acid deficiency in valence electron will accept. Okay, but that's not always true. It can be an acid that has extra. So there is the idea of fixed definition is not. But in general, we say any compound that excess of valence electrons, that's a base. And if it's missing or deficient in valence electron, that's an acid, correct? That's general saying. But then the donation will come of the valence electrons from the base because it has, that's the one has extra valence electrons. So now we'll have connection here between those two. We'll take this one of those here out. Okay, so we'll put one instead is here. We took the second out here. One is here, and then guess what? We'll have a bond here. So this will appear positive because at last one electron. This will appear negative because it gained one negative, correct? So this is acid base, correct definition based on the amount of valence electrons on each of those compounds. If it has excess, that will be a base. If it has the least amount of valence electrons, that will be an acid. Okay, guys, so that's Lewis. Anything about this? Anything? So, and it's the same idea with the conjugate acid conjugate base. It's the same thing, but this time is the acid is not donating its protons, but the base is donating its valence electrons. It's reversed. Any question about this, guys? Any question? Any question? Yes, you have. I see you had a hand there. I see a hand. Rita? I see.
Oh no, my button is stuck. I don't know how to get that off.
No, just go in back to the same same place you get.
Oh,
Click on it. Click on it a couple of times. It will
oh,
disappear. Yes, it
okay.
disappears.
Thank you. Sorry about
Yes.
that.
No, that's fine. So Any question about this Lewis type of definition? Any question? Any question? So now we have to look at the strength of acids and bases. Let me just look at the. No, we have to do. Let me let in here. Students want to. Hold on. Stop sharing here. Let some students coming in. Okay, guys. So I would like to share naming of acids and bases. Naming of acids and bases. So let's share. Share blank. Okay, guys. Okay. Let's share. We'll name those acids first. Well, the acids, you have different types of acids. First, acids without oxygens. Acids without oxygens. So without oxygen. Everybody can see? Okay, without oxygen. Well, those examples like HCl, HBr, HI, and for that HF here. So the first thing to name those type of acid without, okay, without oxygen, you have to name them first by naming first the first element, which is the first element in this case will be, you name the first element here first, okay? The first element is hydrogen, so you name it as, the first element is hydrogen, okay? That's the first thing, hydrogen. And then you add to it then the second element and convert it to IDE. So like, for example, chlorine, fluorine, correct? Fluorine, this is fluorine atom connected to hydrogen and fluorine, correct? So take I and E out. Let me see if I can get another color. Take the I and E out here. Add IDE. So this is hydrogen fluoride. What we call it, hydrogen fluoride. Another one is hydrogen fluoride, chlorine, I N E. Take this the INE out. Add I D E. So this is hydrogen fluoride, hydrogen chloride, hydrogen bromide, hydrogen iodide. That's the first naming of acids without oxygen. Any question about this? Any question about this? Any question, guys? Any question? So
No.
now, okay, now we'll say, let's now, I'm not wiping everything out, but I'll say, just save ourselves time here. This time with, okay, with oxygen, okay? So now I take all this stuff here out. I'll come back and correct for the oxygen here. With oxygen. Well, in this case with oxygen, you have always to look at the middle elements. What's the middle element? Then you put the middle element there as the main name of this acid. Then you'll the end of this uh, combination, you'll add ic acid. So don't worry about the oxygen, don't worry about the hydrogen, don't worry about anything. So that's the beginning. Without oxygen is easy. Hydrogen bromide, hydrogen iodide, hydrogen chloride, correct? So because they are acid, they call sometimes hydrochloric acid, hydrobromic acid, correct? Hydroiodic acid. So you can't name it as either or hydrogen bromide, okay, as normal, or you can name it as specific to the acid, hydro, and then the first for hydrogen, hydro, and the last name is like bromine. Take the INE out. Ic acid, hydrobromic acid, hydrochloric acid, hydroiodic acid. This is when you name it as very direct as an acid. But if you name it in hydrogen bromide, that's correct too. Correct. But when you specify that's really that's an acid, that's easy to name it hydro, not the hydrogen, the whole thing. Hydro, and then bromic acid, hydrochloric acid, hydroiodic acid, hydrofluoric acid. But now with the oxygen, it's a little bit difficult because then the oxygen will come here. We'll have like H2SO4. Well, don't worry about the hydrogen here. They're not part of the naming. We concentrate ourselves on the central atom. This is sulfur, correct? Where's the sulfur as is? And then you add to it iic acid. That's the addition you'll add to it. Okay? This is sulfuric acid. What is this? This is sulfuric acid, according to the middle. So now if we have HNO3, what we call this? We'll come to this, correct? That's nitrogen, correct? Take all those out, OGN out, and then just add ic acid. Always the middle center atom here. It's nitrogen in this case, so that's acid. Nitric acid, HNO3, nitric acid, correct? So I go from the middle, it's nitrogen, take the oxygen out, and then add ic acid, nitric acid. Now, how about if I have something looks, let me clear the whole thing here. How about if I have, how about if I have something looking like this? H3 BO4. So what's the name of this? This is 4 here. Again, we don't care about naming the number of oxygen or hydrogen, whatever, but we do care about what the central atom. So what's the name of this acid? What's the name of this acid? Somebody will tell me? Everybody's with me, or come on, guys. What's the name of this acid? Hello?
I'm not that
Hello?
good at naming these acids.
Well, we said we concentrate ourselves on the central atom, not hydrogen, not oxygen. This is phosphorus, correct? This is the middle.
Yeah.
This is phosphorus, correct? So then what we'll have to do here, you have to come here with OUS out, this phosphorus here out, and then you'll add to it ic acid. This is phosphoric acid. What is that? Phosphoric acid. This is phosphoric acid. Now I want to show you one last one here with different type of amount of oxygen, how the different type of oxygen will change the name of the acid, will really change the name of the acid. So any questions so far? Any questions so far? Okay,
No.
let's do it. Okay,
No
now,
question.
okay, so let's look at the, I have here H C L O4. I have H C L. I want to see the effect of the oxygen. 3. I'm going less and less and less down. H C L O2. And then I'm going down. H C L O. So I have 4 types. I have to have oxygen there, otherwise it will be hydrochloric acid. Like the last one, it has to have, this is one here. You cannot have 0 here, 0 oxygen. It will be just the hydrogen chloride or hydrochloric acid. So now what we say to this, we have to look where is the standard naming for for this acid. All those acids, they have in common the chlorine atom, the hydrogen atom. Both those atoms, they are kept constant, not changing in their amount. However, the oxygen can go from lower to higher, or can goes down, down, down. Highest is 4, lowest is 1. So the problem with the oxygen, so it's affecting the name of this. So we'll take this here being the standard one. This is the standard acid, and it has the central atoms chlorine, so it will be chloric. Chlorine can take the chlorine, will be can take the ion out, will be chloric acid. Now, this is O3, that's your standard. O3, oxygen 3, that's your standard. Maybe you need help with that, so somebody has to help you with this. Which one is standard, which one is not the standard. So in this case, on those four, the hydrogen, chlorine, oxygen acids, they're called multi hydrogen chlorine acids and oxygen acids. So they are having a standard which is oxygen 3 with oxygen 3, our standard called chloric acid. If you go higher, then will be from, you know, the word hyper means high, correct? Hyper, correct? Hyper means higher, very high. You know, the kids have taken a lot of sugars and they are really very hyper. So hyper means, as you know, the blood pressure is so high they cannot control themselves. They start jumping around all over the places. So they will say, okay, we'll take the high out, we'll just take the per what? Perchloric acid. This is called, with the oxygen is 4, perchloric acid. So with the 4 here, of course, this oxygen is hyper, or hyper means more. So it's abbreviated per. This is perchloric acid. Okay. If the oxygen is less than the standard, above the standard, that's called ber. Ber means above the standard. And lower the standard here is 2. The standard is 3, that's 2. That's lower than standard. Will be, instead of chloric, will be what? Chlorous acid. Okay, guys? Now, one less than the chlorous acid, less than the 2, like 1 here, there will be what? Hypo. Hypo. And then this is chlorous. Means less than the chlorous, less oxygen than the chlorous acid. Okay, guys? So this one is this, and this one is this. So this one hypo, you know, hyper, hypo, hyper, hypo. So hypochlorous acid, that means less oxygen than the chlorous acid, that will be hypo. So those are the typical types of chlorine, hydrogen, oxygen. Depending on the amount of oxygen, the name will change accordingly. Okay, guys? So, any question? Any question? Any question?
No.
Okay, so now, no question, then we'll go for the next one. Okay, I'm going to see what we have here. Let's see what we have here. We named all the assets, correct? So let me share with you here. So name with oxygen, without oxygen, and we name all the stuff here. Oxo acid means would have oxygen. So we did that. naming acid and base. So now we will name bases. Any questions so far? So acids. So conjugate acid pair, we did that. Conjugate acid, the word amphoteric, strong acid, strong base. Okay, so let me take stop sharing here and share. We name now bases. Well, the bases is not really difficult. The only thing you have to watch, because the base they can have metals or whatever. It does not have to have, it does not have to have specific stuff to learn the base. The base is easier to name, but you have to watch for the multi-charge. So I have naming a simple one. So we have to look. It is. If I have a metal group of group 1, like sodium, and the OH, so how we name the space? Sodium, you name the first element, and then you name the other OH as hydroxide. So sodium hydroxide, correct? So potassium hydroxide. If I go for group number 2, for example, magnesium as 2, group 2 is valence electrons 2, so this OH is 1, so that's 2. Magnesium hydroxide, that's a base. Calcium hydroxide, that's a base. That's the way we can name them. First the metal, and then the hydroxide. So 2. Okay? Calcium hydroxide. Those the groups. Now, how about if the group, of the metal is found to be in this B groups, meaning within the middle of the of periodic table. Those metals, you have to be careful about the charges they have. Okay, so in order to name this, so I'm gonna give you some examples and then we'll look at this together. So let me take this one here. Now, I have, okay, so copper here in this case is 2. Copper is 2, and the hydroxide is always -1. Always -1. This is 2. So the 2 is given 2 underneath the hydroxide, and the one understood, not written, it will be, it is. So the cover will take the 2 because it's has 2 charges, 2 here, the cover has 2, and the hydroxide is this is 1, this the one here from the cover, and the hydroxide has 1, it's 1 here. So how we name them? Well, you have to get the charge involved in this. So the first one is copper 2 hydroxide. So this is a base called copper. You write it here, but anyway, so copper 2 2 guys, 2 hydroxide. Okay, guys. cover 2 hydroxide. How about the underneath? Will be cover what? The one here from the cover 1 hydroxide. So you have to specify the oxidation number. What is cover? Cover has 2 charges, cover 2 and cover 1 as iron, correct? Multiple charges. So how about this one here? Let me take this one here. You tell me. Here it is, guys. So we have this hydroxide. So how about this one here? Okay, guys, what's the name of the first one? What's the name of the second one? So somebody will tell me. Come on,
Iron
guys.
2 oxide.
Hydroxide. Iron 2 hydroxide, correct. And the second one?
Iron 3.
Hydroxide. That's correct. That's iron 3. So you get the idea. When it comes to multiple charges, bases that have metal with the multiple charges, so you have to name the exact charge on the metal. So the metal will be iron 3 or will be iron 2. So you have to specify whatever it is the compound is. So that's I think we conclude in a very humble contribution, because you will not get a very difficult questions about this. You'll get a general question. So if you are asked about the topic, so you know how to answer them. Let me just take this one out. Okay, so let me okay, so now we'll go for the strength of acids and bases. So let me go back to stop sharing, share. We'll go for acid base. Maybe you can push it if you have time and you are willing to sit maybe to 9:30 or so. So we'll cover most of the stuff, important stuff today. So, and then I will meet Wednesday to finish up the chapter. So here it is. I'm going to show you here. After naming those acids and bases, we know how to name those just with that hydroxide. Some bases, and that's very strange too, they don't have a real name as we can expect. And I mean, it has a name, but it cannot tell us that's a base until really to know it very well. So that's the typical, we talked about a couple of times, the Windex stuff here, this Windex stuff here, ammonia. This is ammonia here with 2 here. 2 this ammonia here, this is a common and a business name, but not the name of the base. So think with me what we can name this one as a base. So ammonia is not really per se, it's mostly, if you go to the store, ammonia, they can sell you a bottle of ammonia dissolved. Ammonia is a gas, by the way, so when it's dissolved in H2O, it will become ammonium hydroxide, which is ammonia gas dissolved in H2O. Otherwise, they will lose all the ammonia as a gas. So they keep it in. So Windex, that's Windex is ammonia, really. is ammonia gas dissolved in H2O to keep ammonia gas dissolved. Otherwise, it will evaporate. So if you have a Windex bottle, don't bring it to the oven or stove or any hot place, because then you will see your Windex ability to clean up glass is gone, because most of the ammonia evaporated from the heat, and your ammonia bottle is mostly is H2O. It's really distilled H2O. There's nothing there. Ammonia is already gone by the heat. So what we name this compound? Somebody will tell me? Give you free 1 minute to Google around and tell me what's the name of it. We said it's according to Brownstein and Lowry, it can accept protons from an acid, correct? Acetic acid, for example. It can accept protons of acetic acid or hydrochloric acid or hydrobromic acid. And according to Luis, said, no. It has extra, that's true. That definition is true, and it acts as such. But then because it has extra valence electrons, it can donate them to some compounds that's deficient in these valence electrons. We call them acid. So the donation comes this time from the ammonia, from the compound that has extra valence electrons available. It's not part of the bonding. Okay, so what we call this compound? Anything? According to Arrhenius, this is what is this? Acid or base? Arrhenius, what is this? Come on, guys, what is
What,
this?
ammonia? Ammonia?
Yeah, yes. Arrhenius, the obsolete concept, the dead concept. What is this? Acid or base?
Acid?
Why is acid? So, according to Arrhenius concept, that's an acid. But we know that's not true. If you have a litmus paper and put the Windex solution on this litmus paper, it will turn red litmus paper to blue.
Oh,
It's
so you
basic,
say
but
it's not an acid, so I guess it's a base.
it is a base. But Arrhenius, according to his concept, any compound that has hydrogen is an acid. Well, look at this. It has not one, it has 3 hydrogens. And it's an acid according to Arrhenius. And that's a big mistake. That's one of the biggest mistakes that you are designing your definition. Acid has to have hydrogen. Well, there's some compounds have more hydrogen, but they are not acids. How about the other one? Here, look at this. That's a phenol here. Pencil ring and OH. Is this an acid or base?
So it's not a base?
That's an acid. That's an acid. That's the
Oh,
base.
okay.
So it can donate its proton. So when you react, let them react to this, ammonia will accept this proton. So that's an acid, this is a base. But what we name this, come on guys, we don't have hydroxide with it. We don't have anything. The common used now, spread out, even IBC maybe
Is that
use
the
it.
Windex you keep talking about?
Yes, that's the Windex. And this is a phenol. I don't know. That's in the bathroom. I smell it in the bathroom. I have to tell my family what that really is. The kids, I don't know that really is. But anyway, that's a phenol. I smell it. I smell this. We have phenol, but I did not check it out. So that's a phenol. This is all this kills bacteria, pickle bacteria, and this has a very distinct bad smell. So too. Anyway, so that's an acid can donate its protons to what? To this base. Anyway, at any rate, this is This is the name. We can't say benzene hydroxide. No, that's a phenol. The whole name is one word called phenol. This is a phenol here, an acid. This is because it has no hydroxide, it has nothing. So just name it as you know. The name of it will be nitrogen trihydride. Nitrogen, nitrogen trihydride, for the people they can't really having in the store, give me a bottle of nitrogen trihydride, what that really is, they have no idea. But tell that person, give me a bottle of Windex, then that person will know what Windex is, but does not know that it's ammonia mixed with H2O, just a distilled H2O. That's normal. So, at any rate, let's see the last topic I wanted to know about the strength of acids and bases. Strengths of acid and bases. So, I can't take all this. I'll tell you just here, and then we'll come back in Wednesday. We'll talk about this in detail. So we have luckily 7 strong acids. That's all. So it's easy to memorize strong acids. So strong acids, and we will describe what we mean by the strength. Strong acids. All the acid found in nature or this universe is weak, very weak, except 7. 7 strong acids. There are from the halogens, hydrochloric, hydrobromic, and hydroiodic. And then you have sulfuric, you have nitric, oops, I have to, nitric, I have to write the structure. Nitric, how many we have? 5. 6 and 7 is perchloric acids, HClO4 and HClO3. So you have 2, 3, and 2. 7 strong acids are available. Only 7 strong acids. All the acids found in this universe, not our just galaxy, in the whole universe, in the whole millions of galaxies, you will have those 7 strong acids. All the other acids are weak. That's easy. So how about bases? Well, it turns out to be that's even easy. So it turns out that's to be easy, and then I'll stop here. So let me take, let's clear this. So instead of strong acid, we write strong bases. Strong bases. So, well, it turns out that's easy because group 1 plus, or groups 1 and 2 in the new periodic table, or in showing the details of valence electrons called 1a plus 2a. those groups, like the first group, for example, first group here, start, I think, with first group. I mean, the first group start with lithium, for example, lithium, sodium, potassium, okay, so cesium, francium. So all this first group, the hydroxide of it, the hydroxide, group 1 and 2, 1A, hydroxide OHs. Those are the strongest bases ever. Those are the strongest bases ever. So group 2 start with the beryllium, beryllium, calcium, and barium, magnesium, here's the magnesium, calcium, and strontium, and all this group until the end. So this francium is far, So group number 1 and 2, those are making strong bases, the hydroxide of them, the hydroxide. All the other other bases are weak. So all the bases found in nature are weak, except group 1 and group 2 hydroxide, metal hydroxide. So those are the only one. That's the only ones are strong, all the others are weak. So I think I will stop here, and I will meet you this coming Wednesday. And thank you for your patience and understanding. So it was a very important appointment in my clinic, so I have to attend it. So I can't miss it. And as you know, like more than I know, to make an appointment with a specialist, you have to wait for a couple months. And if this couple months are gone, then you have to wait another couple months. So no, I waited for this about 2.5 months to have this appointment. So I did not want to lose it. I really apologize, but I have no other choice. So if I missed it, then I have to wait another 2-3 months maybe to get this another second. That's a specialist, not the family doctor, whatever. That's easy to attend. That's not a problem. But the specialist is so hard to get. Those are very hard to get. Okay, so you have to wait for a couple of months to get an appointment. Anyway, so I'll stop here, and then I'll open for any question you have. If you have any question, it's okay. I'm here. Wait for maybe a couple of minutes. If it's not, then I will stop recording, and then we will meet this coming Wednesday. We'll finish up the chapter. I think we are almost there to finish it up. Okay, we have just only the strength. So we know that's now the naming, the all the definitions, how to name acid base. Now we'll go back and look at the strength, what is characteristic of the strength, how we can determine. I gave you the name of the compounds that are strong acids, the name of compound, the strong bases, and all the rest are weak acids and weak bases. But we have to work on it using some math. So with the help of calculation of the acid-base dissociation constant, we will know which one is stronger. That's among the weak. The strong, we know they are strong, but how weak is the word is weak does it mean? So when I say weak acid or weak base, how weak that might be. So we have to look at the weakness and the strength of those acids in details. Okay, any question, guys? Any question? Any question, please ask me. If you don't have any question, I will stop recording. I will see you this coming Wednesday. Okay, guys? Any question? Okay, so we have only 2 left. Any question, guys? Okay. Any question? Jocelyn, you are the only one left. Any question, please? Jocelyn? Jocelyn? Hello? Any question? Well, I think she had left. Uh, I'll just stop recording.